this video, we'll do a quick review of intermolecular forces to help you with Experiment 12B. So in Experiment 12B, we're thinking about intermolecular forces, and this is really just a way for us to think about how individual molecules interact with each other. So we've learned all about bonds, we've learned about ionic and covalent bonds, but what happens once we actually make a molecule? How do they interact with each other? Well, we know that most of the time this happens because protons and electrons make up the molecules, and they're oppositely charged, so they're attracted to each other. How attracted they are depends on the molecule itself and whether it contains partial charges, temporary charges, and really thinking about the size, shape, and polarity of a molecule. So let's review the different intermolecular forces. So when we think about dispersion forces are in everything. If we look at a molecule, essentially what we're seeing at the molecular level is that when electrons move around an atom, sometimes they get stuck on one side, and this leads to a very small partial charge on a molecule, which makes the other side partially positive. And when a bunch of molecules have this happen, they have this attraction between the partial positives and the partial negatives that momentarily crop up. So this is a relatively weak interaction, but it definitely grows with size, meaning the molar mass. So as you get much bigger molecules, the strength of those intermolecular forces gets significantly more noticeable and stronger. What about a dipole-dipole force? So this happens when we have polar molecules that have a net dipole. So this means that the molecule doesn't just sometimes have a temporary partial positive or partial negative, it happens all the time. So this is especially true when we have electronegative elements such as oxygen in a molecule, and we have a net dipole towards those oxygens, so the negative end of one molecule is attracted to the positive end of another molecule. And because that dipole is always there, that attraction is a bit stronger. Then the dispersion force, actually quite a bit stronger and really affects the boiling point of a substance. Then we have hydrogen bonding, and hydrogen bonding is an intermolecular force where in a molecule you have to have H directly bonded to F, O, or N. These are the most electronegative elements on the periodic table. And so when hydrogen is directly connected to these elements, what happens is we have that strong connection, or we have a dipole that arises, okay? And it's especially strong when you have hydrogen involved because it only has one electron. So if that electron's getting pulled away from it by a really electronegative atom, you have that dipole-dipole interaction that becomes even stronger. And so in water molecules, this is a particularly strong interaction because the oxygen has two lone pairs that are attracted to those really positive hydrogen atoms, and it's a pretty strong interaction. So this one is stronger than both dispersion and dipole-dipole, and is especially potent in things like water. Then we have ion dipole, and this is a bit of a different intermolecular force because the other attractions happen in covalent molecules, and this happens when you have an ionic substance that gets added to a polar substance. So you have to have both those individual components in order for that ion dipole force to exist. So this is especially noticeable when you have something ionic like NaCl dissolved in something really polar like water. And so the negative ends of the water molecule are attracted to that positive charge on sodium, which is not a partial charge, it's a full-on charge. And the negative chloride ion would be surrounded by the partial positive part of water and form its own attraction that way. And so this attraction between the ionic substance and the polar substance is an ion-dipole force. And this is the strongest of our intermolecular forces that are possible. So how do we assign the forces? Well, it's based on the structure of the molecule. So all molecules will have dispersion forces. So all have dispersion. Then we decide if our molecule is polar. This is something that we practiced in experiment 11. If the molecule has no net dipole, then it is nonpolar and it won't have dipole-dipole interactions. If the molecule has a net dipole, then it is a polar molecule and it will experience dipole-dipole attractions with other nearby polar molecules. Then looking at our structure, we decide, is H bonded to fluorine, oxygen, or nitrogen? If the answer is yes, then our molecule will exhibit hydrogen bonding with nearby of the same molecule. If the answer is no, then we will have no H bonding. Then, if we're thinking about intermolecular forces and we have both a polar molecule and an ionic molecule, then we will see ion-dipole forces. So for something to be ionic, that means it has a metal plus a nonmetal, or this can be a polyatomic. And for something to be polar means it has a net dipole. And the polar substance we usually choose is something like water or alcohol. So an example of this that we saw above was NaCl in water. We have something ionic, we have something polar, and together between them they will form an ion-dipole force. So another part of this experiment is deciding, will two substances mix together or will one dissolve in another? In order for this to happen, we know that like dissolves like, meaning they have to have similar intermolecular forces. So something nonpolar with only dispersion forces will dissolve in something nonpolar, again with only dispersion forces. Or if you have something polar, it will mix or dissolve in something else polar and form a homogeneous solution because they will be attracted to each other. Our other option is to have something ionic plus something polar because we form that ion-dipole attraction, which is very strong. So this should help you assign the intermolecular forces and decide whether and why two things will mix.